Hello, I'm Graham Horton and welcome to today's video. Now in today's video I'm going to look at a way of actually dimming non-dimmable lights. Now you can tell whether your light is dimmable or not by having a look at the base cap of the lamp or of the packaging that you've got the lamp in. And if you look at this lamp, it says not dimmable. So it's got a dimmer circuit with a cross through it, which means you cannot use this with the standard dimmer control. Now the standard dimmers which this applies to are ones which will change the phase angle at which the bulb is receiving current. So when it's dim, there's very little of the 50 cycle wave going into the bulb, and when it's bright you're getting the whole of the 50 cycle. So it's almost like a phase shift circuit to shift current into the bulb. But because of the design of the bulb, it doesn't allow you to use that sort of phase shift circuit. Now I've got here a circuit which I've put together to allow the dimming of these non-dimmable bulbs in a safe way. There's absolutely no risk of fire or anything like that. It's quite a safe circuit. It's been adopted for years in other applications. I've just modified this to work with these bulbs. To give you an idea of what happens with these bulbs, if you look behind me here, I've got such a non-dimmable bulb. And I've got one of these phase shift type controls here. As I try and dim the light, you'll notice that it starts to flicker and flash. And the lower the voltage, the more that it flickers. So you can't dim these lights, they're not serviceable. But I've got a method here which I want to show you today, which will allow you to dim these lights in fixed increments. Let me just set this up on the bench and I'll show you what I mean. So here on the desktop you can see my device. It's a box which has got 3 capacitors inside. One which is 220 nanofarad, the other is 470 nanofarad, and this one is 1 microfarad. Now I've chose those values to give me specific power for the lamp. We've also got the situation where I can have the lamp on full intensity. The lamp is plugged into this socket and the socket is wired into these 3 switches here. The lamp itself is plugged into the output, and the input for the whole circuit is being monitored by my power meter. So I'm just going to switch on the light at full intensity. So you can see behind me the light is on full brightness, and on the power meter you can make out that it's pulling about 11 watts. It's rated at a 10 watt bulb. It's actually drawing 11.1 watts, 180 volt amps, and that is because of the power factor. If we look at the power factor, these are normally around about 0.5 to 0.6, so this one's 0.62. So because it's a capacitive load, we've got a lagging power factor. Go back to watts, we can see you've got 11.1 watts. So that's with the lamp on full power. Now if I just switch in the 220 nanofarad one, and if we look at my circuit here, you can see that when it's on full, the mains comes in, goes through the normally closed contacts of the switch and straight out to the lamp. So we're getting the full voltage out to the lamp. But when I operate switch 1, which is the one with the 220 nanofarad in, it breaks the circuit taking the full current and passes it through the 220 nanofarad. Now if you saw my previous video on LED floodlights, you see that I use the same circuit. So with a 220 nanofarad capacitor, its reactance is 14.4K. I'll put a link in my video description to the site where you can actually get the reactance for any value of capacitor that you care to choose. So with that 220 nanofarads, its reactance is 14.4K. Now discovered by just measuring the wattage and voltage that the lamp itself has a resistance of 5.8K and is pulling normally 0.41 amps. So we're using that calculation to calculate the new current. So when we've got effectively 14.4K in series with this lamp, the new current is 0.011 amp and the new power using I squared R gives me 0.7 watts. So when the switch S1 is closed, the lamp will light with something like 0.7 watts. So let's have a look at that in the circuitry. If I switch on 270 nanofarads, you can see on my power meter it is indeed dropped to 0.7 watts or 14 volt amps. And if we look back to the lamp itself, you can see that it is much dimmer. So we're running at 0.7 watts, so substantially reduced if you wanted this for, say, a night light. Now I can't switch off the 220 nanofarad because that would then put the full power back onto the circuit. If you had a 4-gang switch, then you could use one of those switches to provide full power and still leave the 3 independent brightness levels. Or in fact, if you had the 3 switches, you can get 7 states of brightness. But with my only 2 switches and this one in a single mode, I've got 5 levels of intensity, which I can dial in. So we're going to leave S1 connected, so that will be still passing 0.7 watts into the circuit. When we add S2 in, the current flowing through that 470 nanofarad, equivalent reactance is 6.7K, so we can work out the new current, and that will be 2.11 watts. So add that with the 0.7 watts of the S1 or the 220 nanofarads, so we should see something like 2.8 or 2.9 watts on this light. So let me switch on S2. We're actually pulling 2.1 watts, and if we look again at the light, it is indeed a little bit brighter. If I just turn that off, you can see it dims. Turn it back on again, it brightens. If we now look at the 1 microfarad, and again we'll leave the lamp illuminated, so if I switch on the 1 microfarad, you can see the lamp again increases in intensity, and if we look at the power level, it's now 4.6 watts. So with the S1 made, the S2 made and the S3 made, we're now pulling about 5.6 watts across the whole circuitry. So we've reduced the power of the lamp from 10 watts to 5.62 watts. If you wanted to change the overall brightness, then you could change the value of these components. So a 1.5 microfarad would pass more current into the lamp, put that 470 nanofarad as 1 microfarad and the 220 as a 470, then you're lifting up the whole brightness. So having a look at the circuit of this device, we need to use what are called X2 rated capacitors. You must use these safety capacitors which have been specifically designed to work at this sort of voltage. Because they're in series with the lamp, we've not got 240 volts directly across the capacitor. We've always got the load there, which is dropping some of the voltage as well. So we're probably working about half the voltage, maybe up to 200 volts across the capacitor, not the 350 that you might expect peak to peak with a full waveform. So providing you're using 370 volt working capacitors, X2 rated, which normally will fail open circuit. If they do fail, then there should be no problem. So if you're going to use this circuit, you can use the capacitance reactance calculator that I've included in the video description below, and also the frequency you can change from 50 Hz to 60 Hz if you're in the States to calculate the new impedance for your particular frequency. Again, it will depend on your wattage of your lamp as to what value of capacity you use to reduce the current to reduce your wattage. So you can see that from this circuit that for my particular case, 10 watts, reducing it to half power, I'm going to be using a 1 microfarad in series with a lamp. So thanks very much for watching. Of course, if you're a new viewer and you're liking these reviews and these presentations, please do hit that subscribe button. It really does help. Also click that bell notification icon and you'll be advised when I upload new videos to this channel. So until the next video, thanks again for watching, and I hope to see you all very, very soon. Goodbye for now.